International Festival of Research and Partnerships. So my name's Lauren Winch and I'm the manager of the International Research Partnerships portfolio at the University of Bristol. And I'm joined here today by my colleagues Samantha Barlow and Eva Makiola, who will be supporting this meeting. So before I hand over to our chair for this session, just a few words of housekeeping. Please ensure that your microphone remains muted unless the chair invites you to speak. This is just to minimise background noise and ensure that everyone can clearly hear the presenter. This session will be recorded and posted on our YouTube channel, which can be accessed from our website, and we'll share a link on the slide at the end. Please ensure that you've added your name rather than being listed as guest, as my team will be monitoring attendees, and we also need to know who's asking questions to our speakers. If you do have a question during the presentation, please write it in the chat window at the bottom of your screen. You can either ask questions there or leave comments, and our chair will get to as many of those as the time allows at the end, but we will wait till the end to address those questions. And when using the chat function, or if you're invited to speak verbally, we just ask you to please be respectful. We do reserve the right to remove anyone whose comments are deemed offensive or derogatory, or who we believe is just kind of gate crashing this to cause trouble, which hopefully won't happen, very occasionally does. So apologies in advance if we have any of those issues, then we will remove anyone of that nature. So without further ado, I'd like to hand over to our former Bristol Benjamin Meaker Distinguished Visiting Professor, Professor Kieron Burke from the University of California in the United States, and also one of his collaborators during his time in Bristol, and today's session chair, who is Professor Bob Evans from the School of Physics.
Thank you.
Thank you.
So it's my pleasure to introduce Kieron Burke, our speaker today, and I'm going to do this by just showing a couple of slides. First, about Kieron. Kieron is Chancellor's Professor of Chemistry and Physics at Irvine, University of California. If you read his website carefully, you'll find that he's Professor of Heretical Physical and Computational Chemistry. He may have more to say about that. His background: Kieron studied in Dublin, and then he moved to the US, did a PhD with Walter Cohen in Santa Barbara. Walter Cohen was indeed one of the founding fathers of density functional theory that Kieron will be telling you about. He then did postdocs in Rutgers, and in Indiana, moved to work with John Perdue, another founding figure in density functional theory in Tulane, became professor in Rutgers, and moved to Irvine in 2006. So of course, Kieron will be telling us what he does, but just a wee bit of background. He's a major figure in developing and applying density functional theory to electronic systems. This means to quantum mechanics, in chemistry, solid state physics, and material science. He's one of the most widely cited authors in the field. A particular paper authored with John Perdue and Enzerhof, usually known just as PBE, from 1996, has that many citations. That is a lot, ladies and gentlemen. In fact, the erratum, which appeared, has more than 3,000 citations, which might be a record for an erratum. His awards are many: Fellow of the American Physical Society, Royal Society for Chemistry, that's UK, American Association for Advancement of Science, and he's an elected member of the International Academy of Quantum Molecular Sciences. He will be telling us about his visit to Bristol in 2019, and of course the collaborations are ongoing. His main host was Professor Fred Manby in chemistry, but he also interacted with the other two hosts, that's Michael Burry and myself, in physics. And of course, this reflects Kieron's diverse research interests. 3 publications from the interactions with the physicists, 2 papers with Michael Burry, this one in 2019, this one in 2020, and then a later paper where I'm a co-author, 2020. Additional activities. Kieron gave an inspiring graduate course called ABC of Ground State DFT. He gave a public lecture. He arranged a fruitful research visit for Dennis Perchak, who actually came, and that helped us in the collaboration in writing this piece of work. He also contributed to a research school in Lausanne. Perhaps most importantly were the interactions aside from strict academia. These were excellent discussions in the pub and over lunch. They were certainly a highlight. So without further ado, Kieron, let me pass over to you, and we're looking forward to hearing what you have to say.
Thanks a million, Bob. And it's a great pleasure to be at least virtually back in Bristol. I had a wonderful time there. And let me share my screen. And yeah, and so what I would like to do is talk a little bit about what went on when I came to visit Bristol. And I had this rather grandiose title, Using Maths, Physics, and Chemistry to Save the World. Now I added a question mark because you can decide for yourselves at the end whether or not we're making any progress on that. So my visit was, hold on, almost started 2 years ago, roughly. I visited both chemistry and the physics departments. I had hoped to be back about a year later, but various events intervened, obviously. Chemistry was primarily my host department, and I was very, very warmly welcomed there by especially all the theoretical faculty that I hung out with and the students. But unexpectedly, as we've seen, a lot of the collaborations ended up in physics and mathematical physics. So highlights of the visit were I had many visitors coming through, both friends and family, as well as some scientific collaborators. They all loved Bristol, and most were unaware of its charms. I was able to tell lots of people about all the great research going on at Bristol. When I was there, people were asking me sort of what I was doing there and so forth. And the accommodation at the principal's house, which had just been renovated, was really fantastic. It was sort of first-rate accommodation, and of course, it's right actually midway, basically between the chemistry and physics departments. So, and it's very easy to get downtown. Okay, the scientific content of what I'm going to talk about is this idea that we these days use electronic structure calculations. The whole world essentially uses electronic structure calculations in almost all aspects of what I consider everyday science. Here are some examples. So I'll explain a little bit about what that is and why it's important. And then I will talk a little bit about chemistry, physics, and mathematics. So this is a picture I like to show. I teach a course about this back home in Irvine here. This is the carbon dioxide content of the atmosphere. And these are careful readings that started about 50 years ago in Hawaii. And you can see that, in fact, even looking at the most recent year, you can barely see any change in the amount of CO2 we're pumping into the atmosphere, which of course is heating the planet. Now, looking at this picture, it looks like maybe it hasn't gone up that fast, that much. So this is the ice core data for the last 10,000 years, coupled with the Hawaii data, and you can see how dramatic this rise is. And I was explaining that part of the reason we know that this is man-made is because we have climate change models, and we can, in those models, turn off the man-made contributions from the Industrial Revolution and see that that when you turn off the amount of CO2 going into the atmosphere, you can see that the warming of the planet doesn't happen. But we need very much better models than we currently have in order to understand much better the climate. Okay, so that's part of why it could be important for saving the planet, is both in modeling climate change, but also in developing all the technology that we're using currently, such as solar power, to reduce CO2 emissions. We'll see that these electronic structure calculations play an ever increasingly important role. Now, this strange looking character is Paul Dirac. He's very, very famous. He was one of the 2 or 3 people who created modern quantum mechanics. And he was actually, I was a bit disappointed to see he's not on the Hall of Fame at the Bristol Physics Department, but it turns out that's because he was in mathematics and he was an undergraduate. But he's one of the most famous physicists of all time. And he famously said that, you know, because we understood quantum mechanics and the Schrodinger equation, that all you need to do is use it to figure out sort of chemistry and materials, but that the equations are a little too hard to solve. And that quote is often stated, but what people don't state is the following part, which is that because of that, it's important to come up with approximate ways of solving these too complicated equations. And in fact, he wrote down one of the very first, what we would now call density functional approximations in the 1931. So the basic problem is we know the rules, the physics rules of quantum mechanics. We know them completely, essentially, for these problems, but the equations are too hard to solve. And the problem we want to solve is for what's called the lowest energy, the ground state of the electrons, in, say, something as the simplest case would be a hydrogen molecule. And here R is the distance between the 2 protons in a hydrogen molecule. And if we could only calculate the binding energy curve that I'm showing here accurately enough, we can deduce lots and lots of properties of the molecule, such as its bond length, the bond energy, how fast it vibrates, and things like this. So this is called a first principles idea, meaning you solve the Schrodinger equation directly. There are no adjustable parameters, and you get out the essentially highly accurate information about the molecule. Now, it's easy to do that for H2, but it gets very hard when you have many electrons in your system. This is too expensive to solve once you have too many electrons, and if you've more than about 10 or 20 atoms in a molecule, we can't do it. So this is why the electronic structure problem is evil. You really need to use quantum mechanics for these electrons. It's called a quantum many-body problem. Every electron sees every other one. And on top of this, chemical accuracy, which is what we call about 1 kilocalorie per mole error, is about 1 part in 10 to the 7. The molecules and materials have a vast amount of electronic energy, but it's tiny changes in that determine sort of chemical bonds and the shapes of molecules and materials. And the traditional methods that we have, which are very good, but the cost grows too rapidly with the size of the system. So the greatest free lunch we ever had was given to us by my now late advisor, Walter Cohn, called density functional theory. And almost 50 years ago, almost 60 years ago now, they proved a theorem showing that you could do it in a much simpler fashion using just the electronic density, which is much simpler than the wave function in the Schrodinger equation. And they wrote down these Cohn-Sham equations, which I'll explain in a moment, which are much easier to solve. And I always show this picture. So this is Walter Cohn here, smiling. at the bottom of the picture. And what they said is, imagine these fictitious electrons that don't repel each other, but are still highly quantum mechanical particles called fermions. So they still obey the rules of quantum mechanics, but they simply don't repel each other. They're not the real electrons of the system. And you can write down an expression for their total energy. And if you require that their density be the same as the real system, you can actually solve a set of equations for these fake electrons that give you the ground state energy and density. And they wrote down the formulas, which allow you to do this. So they write the total energy in terms of something called the exchange correlation energy, and they showed that the forces that these electrons feel can be calculated once you know that. And this picture is of the very simplest system, a helium atom. This is the exact ground state density, and this is the exact what's called a Kohn-Champ potential. If I doubly occupy the 1s orbital in this potential, I get the exact density and energy. So this bypasses solving directly the Schrodinger equation. Now I was going to run a little simulation here, but I don't really dare to, given the computer problems I'm having. So I'll just talk you through a still picture. Imagine the Earth going around the sun and the moon going around the Earth. And this is to give you the idea of how density functional theory works. If you look at the actual trajectory of the moon, you see that it, in fact, doesn't appear to be a circle. That's because it's circling the Earth as it goes around, and it looks more like a cycloid. And the way DFT works is, imagine that the force from the sun were changing in time in exactly the right way to make the moon follow this orbit without having the Earth there at all. If you could figure out how to change the force from the sun in time in exactly that way, you could figure out the exact position of the moon without ever having to solve for where the Earth is. So in this way, having this effective force instead of the real force, you can eliminate the interactions in the problem. Okay. And it turns out that all of our understanding of chemistry is basically along these lines. If you think of a periodic table, we fill up electron energy levels, while our modern understanding is these are what are called Kohn-Champ energy levels. These are these fake electrons with where we occupy the levels, and the Pauli exclusion principle tells you, because they're fermions, that no two electrons can have the same 4 quantum numbers. And pretty much all our understanding of modern science is based on this picture of how electrons behave. But this is a sort of fictitious picture created for this kind of purpose. Okay, so a few quick applications. One is, very recently, high temperature room temperature superconductors were created under high pressure. This is just in the last few months. And this was made possible by predictions from DFT calculations. So these materials were first calculated on the computer and then afterwards made in the lab. And the computer told us that they would be high temperature superconductors. And in fact, they've now gotten to room temperature. Another picture I like to show is this beautiful fish, the Gilt-head Seabream. And this is from the well-known journal in physiology, Frontiers in Physiology. And what they're pointing out here is that when the amount of CO2 in the ocean goes up even just a tiny amount, the sense of smell of this poor fish gets greatly reduced, and then it's more likely to be eaten by predators because it uses the sense of smell to know when the predators are around. And part of this study, which included studying the fish on a farm, was also had electronic structure calculations and calculating the properties of these molecules with density functional theory. And then my last example for the moment is one that I was at a public lecture because I'm very interested in coffee. And this one shows that it's calculations showing the importance of the water that you use to make your coffee with. And it turns out it is important. And this was actually from the Department of Chemistry nearby at the University of Bath. And here's a picture of me doing an experimental test on the results of this calculation. But the idea is that we can now do increasing amounts of this kind of science by running the calculations on the computer, but they're limited by how many atoms we can put in a molecule. No matter how large our computer is, we run out of steam eventually because quantum mechanics is hard to solve. So what's not to like with these applications? Again, this is from Bristol. This is a density functional calculation for a very large molecule and trying to calculate a reaction barrier. And we see that if we run many different density functionals, we unfortunately get significantly different answers. These errors are totally unacceptable in something called a reaction barrier. They would totally change the rate of a reaction. And in this application, they very cleverly, they replace the key part of the molecule where the chemistry is going on with a traditional calculation. And you see in the bottom, when they do that, when they're able to figure out how to do that, then all these density functional calculations end up giving you the same answer. So then you know that you can trust the answer. So the problem is that we have far too many approximations in density functional theory. And here's another example, again from the chemistry department, where people are calculating these reaction rates to go into models of the climate. So this is an increasing activity. People really need these reaction rates, especially to understand aerosols, small particles, to understand clouds and their effect on the climate. There are very many chemical reactions. There's no way to measure them all experimentally. You need to calculate them. The size of the particles means it has to be density functional theory, but can you trust the answer? And so the problem is that this small little piece of the energy, the exchange correlation energy, we don't have reliable, accurate formulas for. The first formula that Walter wrote down in '65 was good enough for a lot of applications for solids, but not good enough for chemistry. And our present formulas are only they give you useful accuracy, but not chemical accuracy for chemistry and materials. So we have this alphabet soup of many different functional approximations, and then it turns into a mess of which one do you trust under which circumstances. And in fact, a modern DFT conference, I use this picture to illustrate it. What we're doing is looking for the best version of this formula. So we're told we can prove mathematically that a formula exists, but we don't know what it is. And imagine the effect it would have if we could do a much better job on these formulas. Okay, so that's the background to my time at Bristol. So let me explain sort of what happened. And there were two major lines of research that came out. One was, well, my hosts, as we said, there was Fred in chemistry and our chair today, Bob. And then I couldn't resist. I found a very nice picture of Michael on the web. And any resemblance between these three characters and the three I've just shown you is purely coincidental. Okay, so we're going to do a little bit of physics. So Bob Evans is a very distinguished physicist, and he was the creator of modern classical density functional theory. So classical density functional theory is a version of the theory applied to liquids at finite temperatures. There's no quantum mechanics in it, and it solves totally different problems to the electronic version, the one that I've been telling you about. And here's pictures from a Physics Today article that he co-wrote a couple of years ago, about the time that I was there. And these are all different systems, from sort of colloids to even collections of fish, to which you can apply this classical density functional theory. It tells you about the distribution of the molecules in a liquid as opposed to the electrons in a molecule. But he has never worked on electronic problems before. Now, our connection is through something we call warm dense matter. If you take an electronic problem and you turn up the temperature, there are all sorts of interesting things happen, and it's become very important for things like understanding the interior of large planets. So this picture here is a little satellite that goes around Jupiter, and they use it to measure the gravity and especially to try to understand the core. And they're running DFT calculations at high temperatures to simulate the conditions in the core and try to understand what's going on. So as you turn up the temperature, and this is a pretty high temperatures, say of the order of 1,000,000 degrees, and in some cases, here it's maybe 100,000, then of course the electrons begin to behave more like classical particles than quantum particles. And that's where Bob's expertise came in. So Bob mentioned our friend Dennis Perchak came to visit and talk about this blue electron idea, which I'll explain. So we're stitching together, and I stole these slides from Dennis, and Dennis came, and here's a nice picture of him outside the cathedral, I think. And of course, whenever Dennis gives a talk, we also see Jerry, his dog. And so what Dennis was talking about was a concept of using a classical idea in quantum problems. And the classical idea is this. So suppose you have a gas of particles classically, and even a very simple uniform gas, well, they were electrons, but let's say they're classical particles. And instead of looking at it the usual way, you imagine that you can sit on one of the particles and pretend that that's an external force on all the remaining particles. And in doing that, you can make a relation between the inhomogeneous system of you sitting on the blue dot, looking at all the others, and you can relate that to the properties of the homogeneous system where they're all orange. And the reason you can do that is because they're distinguishable, so it's perfectly allowed to sit on one of these particles. But when I suggested to Fred in chemistry that we would do a quantum calculation this way, he was totally horrified because, of course, electrons are quantum particles, they're indistinguishable, and you're absolutely not allowed to sit on one or the other. But it turned out after lots of hard work and a few tricks, we were able to do that. And then this paper finally got published, I guess, just toward the end of last year. Well, when I say finally got published, we finally got all the work done, where we could actually formally prove that you could do this in principle exactly. So starting from a purely classical idea, you could get a new way of doing density functional calculations that is a little more expensive than standard density functional calculations, but a lot more accurate. And in particular, Dennis was able to recover the uniform electron gas at 0 temperature. Others were able to show that you could dissociate a hydrogen atom correctly, which is a hard thing for a standard density functional. And then, of course, when we turn on the temperature, we also get very accurate results. And that's where Bob's expertise comes in, because we could show that, for example, we get the classical results for very high temperatures. So now I'll just quickly turn to more mathematical things. This is again in the physics department, but from my point of view, it's mathematics. So this is Michael Berry, who, well, that picture wasn't supposed to appear yet. I'll explain it in a minute. So you may have heard of him from Mr. Asymptotics would be one way to call him. So asymptotics are a fairly high-level mathematical subject that he really helped develop over the course of his career. you may have heard of the Berry phase. That is Michael Berry. This picture is from winning the Ig Nobel Prize with Andre Geim for levitating a frog. This picture is Michael started out by looking at spinning tops being levitated. And I can vouch for the fact that when I was teaching about 10 years ago, a general course in chemistry, I was looking at high school textbooks, and the levitating frog appeared in the high school textbooks in chemistry. But what you may know less about is he in his misspent youth, he studied semi-classics and quantum chaos. Okay, so now one other subject that I tend to study is machine learning. So I felt I had to show this picture. So this picture I grabbed off the web. It seems to be Michael Berry getting something from the Queen, but we can be certain that this must be a deep fake, because for one thing, the Queen is still smiling and Michael is not actually arguing with her, right? Okay, so what did we do together? So for almost 100 years, 100 years ago, around the time that quantum mechanics began, it was written down something called the WKB method. And it's a way of getting the energies in simple problems without solving the Schrodinger equation. And you write down a very simple integral. This is the energy here. This is the potential in your problem. This is for the one-dimensional case. And so this is really the integral x times p, the classical momentum. So you're quantizing the classical action, and you set it equal to proportional to the Planck's constant times the index of your level, let's say. So this is a semi-classical approximation to quantum mechanics. It's not much in use anymore because we have modern computers. As the level, the quantum level goes up, the approximation gets better. It's really just the first term in an infinite series. The series is often asymptotic, which means that if you add up all the terms, it will diverge. So you have to be really careful. And the Bohr theory of atoms that predated the Schrodinger equation was a version of this applied to the angular momentum. So this is a very old, well-known procedure, but one of the problems with it is very hard to figure out what the errors are in the approximation. And for these electronic structure problems, you would really like to be able to control the errors, as we've seen. So imagine one of these electronic problems has a very simple cone-sham potential. So you're trying to solve for these fake electrons, and we'll pretend that they're in one dimension, and the potential is just proportional to x. There's a hard wall here, and here's our potential. And we get a bunch of energy levels. And here, just for simplicity, we'll occupy them with same spin electrons. So I've occupied the first 10. It's as if we had neon or something. We have 10 electrons in our system, and we occupy the first 10 levels. And then the energy, these are non-interacting electrons, will just be the sum of the eigenvalues that we get from solving the differential equation. Okay, so the key observation in what we did was that, well, you can create a semi-classical approximation not for the individual levels, but for the sum of these levels. It's not the same as the sum of these semi-classical eigenvalues. It's very different. And in particular, so this is the sum of the levels from one of our papers, and you sum all the levels up to infinity, and then subtract down the sum going back down again. But the crucial part is that instead of the index being n here, it is n plus 1. You subtract off all the levels above you. But this n plus 1 is very important because it is higher in energy than the end that you're trying to sum, and our approximations get better the higher you go in energy. Now, I would never have dared to do this by myself, because this sum to infinity, you might realize, is a very large number. In fact, it diverges, but when you're with Michael, you can play those kinds of tricks. So if that sort of disturbs you, it's, you know, very elementary. You just sum 1 + 2 + 3, things like that, and you know that they end up adding up to -1/12. So if you want to figure out how that can possibly be, there's a great blog post by Terry Tao, one of the top mathematicians. Okay, so anyway, so we do this analysis of these methods, and I'm going to use Hartree atomic units here. So in these units, a hydrogen atom has the electron in the hydrogen atom is exactly -1/2. So how good are the new approximations that Michael and I were able to write down? So for those 10 electrons in that well, the exact answer here is 81.513 Hartrees, and the approximation we wrote down, you can see, agrees to the first 3 digits. So 3 digits is very good by density functional standards. That means it's right to within 1 millihartree, which is smaller than a kilocalorie per mole. So this meets the conventional definition of being chemically accurate. But of course, it's a very simple problem, so we can actually calculate the numbers more accurately. So you can calculate 3 more digits, which brings it down to what are called microhartrees. And you see the approximation is actually very good to those 3 more digits. But then things get a little strange when you go to the nanohartree level, and you see that the approximation is still working rather well. And then they get very strange, because you add 3 more digits, and 3 more digits, and 3 more digits, and so on, and so on, and so on, until eventually, if you can do your arithmetic to that level of accuracy, you discover that we have a very tiny error in our approximation, right? That error is of the order of 10 to the -33. So for somebody who's used to electronic structure calculations, it is unfathomable how we could write down an approximation that accurate. And so the difference is in the 33rd digit. And we even understand why it's down there, because we have 10 particles and we do this optimal truncation of an asymptotic series. You can show that the best truncation will be after 33 orders, which is your 33 digits. And even this 3/4 here is a Maslov index, because we have 1 hard wall and 1 turning point. So we can understand exactly why this approximation works as well as it does. And even for 1 particle, it's much better than the original approximation, which, when you think about it, is very funny. We sum up the first 1 levels, as in there is only 1 level. We haven't done any sum, and yet still we get better results. And this is the magic of working with Michael. So what did this lead to? So papers so far, we've heard about a few. So one, Faraday discussion. So some of them are in chemistry, some of them are in physics. Most of them are published in Britain. Here's some of the works with Michael. So the ones with Michael tend to be in the physics journals, without him in chemistry. Here's one from a graduate student of mine working more on this topic. That's the one with Bob. And then just overnight, I think, on the archive, Pavel Oken, a graduate student with me, has written a very long thing explaining the relationship between DFT and semi-classics. Okay, so I'm going to wrap up here with life in Bristol that I enjoyed very much. Here is a collage of photos that I found in my account from all the days at Bristol. Everything was beautiful. Many of you will recognize some of the iconic pictures of Bristol. In here, by the way, there is something that isn't in Bristol. I don't know if people can figure out what it is and where it was taken. And then also here are some views of Bristol. One of my children is a painter, and so made some nice pictures while we were there. And then, of course, this is, of course, another nice aspect of being in Bristol. Now, there may be a certain theme to these pictures, and notice in particular the white rabbit. So Dennis would say that at the end of every evening when he came to visit us, and Dennis had the interesting experience of staying at the Toad Lodge, but the end of every evening ended up with Bob saying, well, how about a pint, Kieron? So scientific summary. So DFT is being used all over the world, 50,000 papers a year. It consumes about a third of all supercomputer resources. It is possibly the largest single method being used on the planet today. It's very likely to become vital over the next few years in climate modeling, and people are using it in little bits already for things like COVID, but it's currently of limited accuracy and efficiency. And there's no way to derive the approximations. And people believe there are limitations on the possible accuracy. So with Bob, we were able to develop an entirely new approach inspired by classical ideas. And then with Michael, invented new approaches to this whole problem. Now, of course, the examples I showed you with Michael are very, very simple. There's a huge amount of work to try to use those techniques in realistic electronic structure problems. But if we could, then maybe we could get DFT to be much higher accuracy, and that would have an enormous impact on all those calculations that are going on all over the world. So with that, I'd like to finish up. And of course, to thank the University of Bristol for that visiting professorship, and to you guys for your attention. Thank you very much.
Thank you very much, Kieron, for a splendid talk. We do have some time for questions. I'm looking in the chat and I don't see any, but please unmute and put your hand up if you do have questions. Kieron, perhaps while we're waiting, could you say a little bit more about the hydrides and the superconductivity? I'm not sure I'd seen that paper.
Yes, so about 30 years ago, a very well-known physicist, Neil Ashcroft at Cornell, suggested that under high pressure, light elements, hydrides and those containing lithium, under sufficiently high pressure would go superconducting and would have much higher temperatures than things at regular pressures. So this is BCS type superconductivity. So based on his ideas, a Chinese group about 10 years ago used a sort of genetic algorithm to search among sort of his intuitive guesses to see if they could find materials that they would suggest would have very high temperatures. And the reason you have to do a very detailed search is because the chemistry is all different and odd under these extreme pressures. So these are very high pressures, 250 gigapascals. And but they made predictions for especially hydrogen sulfide was the case that they suggested. And then a couple of years later, a group in Germany were able to make it under the high pressure, measure the temperature, and it was 180 Kelvin. So much higher than anything anyone had ever gotten before. And then over the last maybe 4 or 5 years, they have slowly predicted other materials, lanthanum hydrides, and now these most recent ones, they are now room temperature superconductors. Of course, for practical purposes, it's not so good because They are room temperature superconductors, but you need an awful lot of pressure to make them. So who knows what the applications will be. But of course, again, many people are now working on finding room temperature superconductors that require less pressure to make them.
Thank you. Other questions? Perhaps I could have another one then, Kieron. I know you were one of the pioneers in introducing machine learning into looking for new functionals and better functionals. What's the current state of play for electronic DFT?
So at the moment, I'm actually participating in a meeting at Los Alamos, studying exactly this question. We're able to make some approximations that are a little better than the human designed ones, but entirely based on the human ideas. We are not able yet to make totally new approximations that will work for many systems, that they talk about whether or not they generalize. So there hasn't been a general purpose functional made yet using machine learning. What has been going on and has been rather successful is people they do these DFT calculations for test systems, and they create new force fields, much more sophisticated force fields than we had before. And these force fields are more accurate and can then be applied, to much faster, bigger calculations. And recently, some friends won a prize for doing a calculation with 100 million atoms using, sort of on the fly, learning these force fields from the DFT calculations and then applying them to enormous systems. So that looks like it might be a huge breakthrough in covering sort of length scales by using the DFT to make the forces and then just doing classical force field calculations.
Thanks, Kieron. There's some questions coming in through the chat now. So okay. The first one is from Adrian Mulholland. Can you see it, or I can read it out, Kieron?
Let me see if I can get to the. So Adrian is asking about, when do we get to see these things being implemented and applied to the climate and fish, etc., right? And he likes the fact that these are fundamental developments as opposed to machine learning. And Adrian is in the chemistry department at Bristol. So as far as the climate is concerned, I think over the next 5 years, there'll be just a huge demand for these kinetic rate constants. The way climate scientists model these things is they need rates of reaction. So you take a little aerosol particle in, let's say, in the troposphere, and it's very dirty, and it has lots of organic stuff on top of it, and it's a huge sort of mess of chemistry. But people have developed models. Once they know the rates of reaction, they can figure out how this particle evolves. And so once you have these rates of reaction, and they have to be very accurate, then you can figure out how these aerosol particles behave. And that behavior can then be fed into the climate models. And a big part of the uncertainty in the climate models is aerosols and the chemistry that's going on top of them. So you can see that people are now already running DFT calculations for these reaction rates, but they're going to be hindered by the fact that they're not accurate enough. So I would say over the next 5 years, you'll see a lot of this going on, but they will need the methods that have been developed at Bristol, where you need to do something rather expensive to make the reaction energy more reliable, the height of a barrier more accurate and more reliable. So this will hinder all of that. But if we could get more accurate functionals, you'd be able to do this much more easily.
Thank you, Kieron. There's a further question. I just see initials, BJCBR. Can you read that one?
Yes, so it asks about how might this apply to quantum computing? So this is a very hot topic, quantum computing, and all over the planet, people are investing very heavily in quantum computers. Unfortunately, our current round of quantum computers, the one that, say, Google was talking about last year, is about 50 noisy qubits. Estimates show that if you really want to solve an accurately an interesting quantum chemical problem, you need something of the order of 1 million qubits that are less noisy than the current ones. So people have high hopes for quantum computing, but to use them in at least the way we currently do quantum chemistry, you can do one-off calculations if you have a large enough quantum computer for what are called strongly correlated systems, for which the functionals do badly, and that'll be useful. But for routine uses, which is really what this theory is used for mostly, it looks like it could be 20 years before quantum computers get to a point where there are enough qubits and they are relatively noise-free in order to be able to really make a contribution. And again, I think on Thursday morning, we're meeting with a chemical company who are very interested in quantum computing, but we'll be talking about the limitations of it for doing real quantum chemistry.
Thanks, Kieron. Mike Ashfold has a comment and a question. Could you unmute, Mike?
You hear me?
Yep.
Yes.
Fine, thank you very much. Kieron, I'm just hopeless at typing intelligent questions, but it's a beautiful talk, thank you. During my career in laser chemistry, there's another example. It's not as important as the one you were highlighting, but there's a molecule called beta phase of barium borate that everybody uses as a nonlinear optical material now in their laser frequency conversion experiments. And that was predicted by DFT. And then some Chinese scientists grew it. And now it's in every laser. So you'd need to look in the literature about 25 years ago, probably, for this beta barium borate. So that was a predicted material that absolutely works beautifully. The question I had, it's the same question. It's a variation of the question I asked you when you gave your lecture in chemistry. But if you're thinking about solar light harvesting, or one of the things we've been playing with recently is trying to make sunscreen molecules that work better. You need excited state chemical physics as well. And I keep nagging people like you. You're focusing more and more on getting absolute precision for ground states, but that's only part of chemistry. So would you like to tell me any more about progress for excited state chemistry?
Yes, so there is this, so I talked entirely about ground states, right? But actually I've spent, quite a lot of time with a good friend of mine, Hardy Gross, who invented time-dependent density functional theory. And it worked, it's applied for excited states. However, right, it's sort of limited to low-line excitations, and it is not as accurate as ground state DFT. Often you look at a spectrum of a fairly large molecule, and you don't need to have that much accuracy to be able to identify what the important excitations are. And so TD-DFT for linear response is pretty developed, is pretty good, but it has some standard holes like charge transfer excitations and things like that. One of the things that's missing is something called the frequency dependence. that's missing from our present functionals. And people have been working, and I worked hard over the last 20 years trying to figure out ways to put it in, and we haven't really succeeded so far. So TD-DFT is useful for a lot of routine low-line excitations, but it is not at a point where, for nonlinear response, that it gives you sort of the accuracy that you might often want. And there is a big push afoot to couple it better to the nuclear motion, which will ultimately mean that you can do things like, conical intersections and avoided crossings. But, when you're dealing with those kinds of objects, you have to worry about this little obscure thing called a Berry phase. I don't know if you've heard of it. Yeah.
Thank you, Kieron. Are there any final questions? We're coming close to closing time. If not, then let me draw matters to a conclusion by thanking, on behalf of all of you, Kieron one more time.
Thank you. And again, my apologies for the some of the internet issues. I don't know what caused them. Yeah.
Thanks very much, Kieron. Enjoyed that enormously.
You're welcome, Michael.